In this chapter, for each wheel that was tested, we'll look at the unloaded spoke tension and then the loaded spoke tension at each position in the wheel and do some comparisons and also some calculations. This is wheel 1 unloaded, and I have gotten all of those 12 dry side spokes to exactly the same starting tension. My tensiometer reading gives me a tension at each spoke of 3.16, which I have to convert into newtons. This is the conversion table for my Supreme tensiometer. You see quite a range of different spokes across the top. And we're really, in this case, interested in the last 3 columns to the left, where we measure newtons, kilograms, and then the dimensionless number that I get for the G14 2mm straight gauge spoke. So I have to do some interpolation and make sure that I recognize that this is not a linear relationship in converting the dimensionless number from the tensiometer into newtons of tension. My tension reading of 3.16 converts to 798 newtons. But I want to show you how I got that number, and we're going to focus on this part of our conversion table here. My average tension reading of 3.16 is going to be between 3.14 and 3.29, so my average tension is going to be between these two numbers here. And in this space, I'm going to do a calculation which is called interpolation to find out what the tension in newtons should be. My tension range in newtons in this portion of the table goes from 785 to 883, which is 98 units. My tension readings go from 3.14 to 3.29, which is 0.15 units. My average tension of 3.16 is 0.02 from 3.14, which is 13.3% of the distance between 3.14 and 3.29. So I'm going to apply that same percentage over here, and that gives me an interpolated value for the tension of 798 newtons. I won't show you the calculations for all the information in this chapter, but I've had to do this interpolation several hundred times. My objective of building a test wheel with a tension of 784 newtons was pretty well met with one with 798 newtons. Here we see the tension readings put into our graphic for each spoke on the unloaded wheel, and we have that to compare to the loaded wheel. Let's now look at the results of the tension measurements on the vertically loaded wheel. Throughout this chapter, the load applied will always be 240 pounds. And these are the averages at each of those positions of the actual tensiometer readings using my Supreme tensiometer. And remember, these are 2mm straight gauge spokes. And these are the average tensions at each position in newtons. We want to do a side-by-side comparison of these two wheels, and the first thing I'm going to do is to remove those arrows on the graph on the right just to make it less cluttered. There, that looks better. One interesting observation right off the bat is if I add up the total tension on the unloaded wheel on the left, I get 9,576 newtons. If I likewise add up all the tension on the loaded wheel, I get 9,388 newtons, which is a delta of only about 2%, certainly well within experimental error. So a fair observation at this point is that whereas the tension in the loaded wheel has been redistributed, the total tension within the wheel remains about the same. If we look at percentage changes in tension, we see that the spoke at the bottom that goes through the load-bearing zone sees a precipitous drop in tension. In every other case, the change is relatively small. The two spokes on either side of the spoke at the very bottom, this one here at 150 degrees, this one at 210 degrees, obviously also see decreases in tension because they are right next to the load-bearing zone, but not as much as the one that's directly at the bottom of it. And in the upcoming slides with the other wheels, you'll see this pattern repeat again and again. This shows us wheel 2 unloaded. Notice that we're using race spokes, 1.8 millimeters in the midsection, and let's look and see what kind of tension readings we get in this case. I have carefully balanced out the tension so that I get a reading of 2.45 for the race spoke at each position. I look up the tension for a reading of 2.45 on my tensiometer conversion table. 2.45 converts to 785 newtons, and that's pretty darn close to the 784, which was my target. So we have 785 newtons on each of the drive side spokes in the unloaded wheel. Let's now look at the results of the tension measurements on the vertically loaded wheel. For wheel 2, using my Supreme race spokes, which are 1.8 millimeters in the middle and 2 millimeters on either end, I get these tension readings in terms of readings from the tensiometer. And these are the average tensions at each position in newtons. Let's do another side-by-side comparison of the unloaded and loaded wheel. Total tension on my unloaded wheel is 9,420 newtons. The total on my loaded wheel, 9,350 newtons, a delta of less than 1%. Here are the percentage changes of the spokes at each position on the average, and once again we see the biggest change is at the spoke that is at the bottom of the load-bearing zone. This will be wheel 3 with my Supreme laser spokes. For the unloaded wheel with the laser spoke, I get tension readings at each location of 1.91. Looking at my conversion table for the laser spoke, this gives me a tension of 837 newtons, which was pretty close to my target of 784. And here it is for each spoke. Now we look at the tension on the spokes when the wheel is vertically loaded. These are my tensiometer readings for the laser spoke. And these are the average tensions at each position in newtons. Another side-by-side comparison, this time of wheel 3. The total tension for the wheel on the left is 10,044 newtons, and the total tension for the wheel on the right is 10,333 newtons, a delta of 2.9%. And just as we saw in the first two wheel studies, the spoke where there is the greatest change of tension is once again this precipitous drop as the spoke goes through the load-bearing zone. As an aside, let's go back to look at wheel 1, unloaded and loaded, and look at these two spokes right here that are at the bottom of the load-bearing zone. If I consider this spoke here and what happens to it if in a loaded situation as it goes under the bottom of the load-bearing zone and it loses tension due to compression, I should see an increase in the cross-sectional area of that spoke, which I can measure with this high-end Mitutoyo micrometer, which is accurate to millimeters to 3 decimal places. And when I measure that, I get the spoke on the left here using this 2 millimeter spoke in wheel 1. I find that my average diameter in the unloaded wheel is 2.010 millimeters, plus or minus 0.2%. And over here in the loaded situation, I have 2.014 millimeters plus or minus 0.1%. So these are really pretty accurate readings. There's the diameter. Half that is, of course, the radius. Note that I have the radius to 4 significant figures, so I'm going to square that number and multiply that by pi also to 4 significant figures, and that gives me a area on the left of 3.173 square millimeters, and on the right 3.186 square millimeters, which is an increase of 0.41%. That's not a big increase in cross-sectional area, but I also don't have a big decrease in the length of the spoke, so it's probably within the ballpark of what I would expect to calculate. Here is wheel 4, once again a deep V, and once again the same leader spokes as we used in wheel 1, but this time we're cranking up the tension to about 130 kilograms of force, or 1,274 newtons, and I get readings on my tensiometer of 3.73 at each location. That converts to 1,273 newtons, which we will show at each location for the unloaded wheel. Now we measure under a vertical load and get these new readings. And those translate into the average force readings on every spoke of the number of newtons shown. Doing a side-by-side comparison, the wheel on the left has a total tension of 15,300 newtons. On the right, total tension of 15,622 newtons and a delta of 2.1%. Here is our percentage comparison. We can see how the spokes change in terms of their percentage increase or decrease at each position of the wheel. Note that the spoke at the bottom of the load-bearing zone sees a 22% reduction in its tension. This same wheel a minute ago at a lower average tension saw a 53% reduction of tension for that same spoke. Here is wheel 5 unloaded, still a DV. Race spokes this time and high tension targeted, and we get tension readings on each spoke of 3.18, and that translates to 1,295 newtons from the conversion table. Here is 1,295 newtons on each spoke of the unloaded wheel. We load the wheel, and we get these readings under load. Remember that each one of those numbers shown is the average of 12 different measurements made at each position. The average tension at each position in newtons. Side-by-side comparison, 15,540 newtons in the unloaded wheel. A total of 16,026 newtons measured in the loaded wheel gives me a delta of 3.1%. These are the average percent changes in tension at each position on wheel 5. Continuing, this is wheel 6 unloaded, deep V, laser spokes this time, high tension, readings on my tensiometer at each location of 2.52, which translates to 1,275 newtons. All the spokes on the unloaded starting wheel are 1275. Put a big load on the wheel. Get these new tension readings with these measurements of tension in newtons. Total tension on my unloaded wheel adds up to 15,300 newtons. On my loaded wheel, 15,548 newtons with a delta of 1.6%. And the percentage changes in tension at each position. Now, as I prepared to conduct experiments on my cross-spoke wheel, I realized there are two ways I can orient the wheel. One is shown there, where the spokes are parallel, straight up and down in this position, but they are not in the load-bearing zone. The other way is where they're at an angle like this, where the end of the spoke where the nipple is right in the middle of the load-bearing zone, and this is going to give us better readings. So I will still read my tension readings of this wheel at the same points. With wheel 7, I'm still using the deep V, still 24 spokes, but a 2-cross pattern on both sides with race spokes and high tension, and I get tension readings on each spoke of 3.13, and that is 1254 newtons. 1254 on each spoke of the unloaded wheel. Under load, I get these readings, and these values for tension. The side-by-side comparison for wheel 7 shows a total of 15,048 newtons on the left, 15,584 newtons on the right, a delta of 3.6%. And the percentages at each location for my change in spoke tension. Wheel 8 is exactly like wheel 7, except we're using a velocity fusion rim instead of a deep V, and I get tension readings at each location of 3.08, which is 1219 newtons. 1219 on every spoke to start with. After applying a load, I get these tension readings in terms of my dimensionless reading on my tensiometer, which converts to these tension readings in newtons. Side-by-side comparison, wheel 8 unloaded on the left, a total of 14,628 newtons. On the right, 14,989 newtons, and that's a delta of 2.5%. Average percentage change in tension at each position. Here is wheel 9 unloaded. It's a velocity DV, 32 holes. We see 16 spokes on the left, so we have 16 measurements we have to make every time we rotate the wheel. 3 cross on both sides, race spokes, high tension, and starting tension of 3.11 on my tensiometer at every location, and that is 1240 newtons. 1240 newtons on every drive side spoke to start with. My tension readings when the wheel is under a load, and those values converted to newtons. Here's my side-by-side comparison. My total tension on the unloaded wheel on the left is 19,840 newtons. On my loaded wheel on the right, 19,865 newtons, which is a delta of about 0.1%. Here are my percentage changes in tension, which we'll come back and analyze in the next chapter. Here's the data for wheel 10 unloaded. It's a velocity fusion rim, 32 holes, 3 cross, race spokes, high tension, and my tension readings to start with are 3.06, and that corresponds to 1205 newtons. Showing 1205 newtons on every starting spoke before the wheel is loaded. And here are my average tensiometer readings for each of the 16 locations around the circle. Here it is in newtons. Once again, a side-by-side comparison. Total tension on the left, 19,280 newtons. Total tension on the right, 19,532 newtons. Delta of 1.3%. And percent changes at each location between the unloaded and loaded wheel. Here is wheel 11 unloaded. Wheel 11 is a Knox composite carbon fiber rim from Knox Composites in Knoxville, Tennessee. 32 holes, 3 cross, race spokes, nice high tension. I have tension readings at each location of 3.10, which is 1233 newtons. 1233 newtons on each spoke. With the load applied, I get these readings with my tensiometer, which converts to the average reading at each location of the number of newtons shown. My unloaded wheel has a total tension of 19,728 newtons, and my loaded wheel has a total tension of 19,993 newtons with a delta of 1.3%. Obviously, the tension on these spokes in total is higher because there are 16 spokes on the drive side instead of 12. And my tension readings of the loaded wheel in comparison to the unloaded wheel. Let's go back to wheel 1 and take a look and see what happens to the tension on the non-drive side. And wheel 1, you'll recall, is using the Velocity Deep V, 24 holes, radial lacing, the straight gauge 2mm leader spoke, and this one is set at low tension. The tension on the non-drive side is going to be whatever is required to dish the wheel, but it's certainly going to be less than the drive side, so whatever kind of swing and tension we've seen on the drive side spokes, we can expect to see even more of that on the non-drive side. We will measure the non-drive side tension in the same way at the same points. Because the starting tension is so low, it's not easy to balance it out and get consistency, but I did a pretty good job, and I have an average of 2.47, which translates to 325 newtons or 33 kilograms of force. We'll show a consistent starting tension on the unloaded wheel. And these are my average tension readings for averaging 12 measurements at each position in the loaded wheel. For my conversion table, I can get these measurements of force in newtons. If you look at the spoke at the 180-degree point, I had to estimate this at about 100 newtons because it's so low that it's off the conversion chart. My total tension on the unloaded wheel is 3,900 newtons. On my loaded wheel, the total is something like 4,181 with a delta of 7.2%, which I think is not bad given the difficulty of accurate conversions of tension at such low levels. Here we see the percentage changes, and if you look at the spoke at 150 degrees, it's at 361 newtons, and then at the bottom of the load-bearing zone drops all the way to an estimated 100, and then back up to 374, so there's a pretty substantial swing in the tension. On the sides of the wheel, we see pretty substantial increases in the percentage of tension, and that may indicate that the wheel is attempting to bulge out slightly into an out of round shape.